Hello and welcome to Geometry Within Engineering by myself, Nicholas Kelly. I'm going to just start off by sort of giving you an overview, and today I want to talk about how engineering really is affected by your geometry, and one of the starts of that, you can see it all the way throughout history, from the Great Pyramids of Giza all the way up to the Eiffel Tower, which are thousands of years apart. You can still see this form of geometry being used in every aspect of engineering at its finest, even from the very humble beginnings that it came from with our ancestors. And so, as you can see, geometry is this real big center point. Anyway, so today I can't get on everything about engineering, but I'm going to be talking about something I've personally had a lot of experience with when I was studying architecture, and that was roofing, truss systems, and sort of construction systems within residential housing and that sort of thing. And an example of geometry in mathematics is ultimately this kind of engineering. And as you can see to the right of the presentation, you can see the different kinds of named truss systems and how they all each use these triangles as a way to provide structural integrity to the roof, and they're all trying to support each other and so on and so forth. And you might think that these are kind of random, but they're actually very, very calculated. These triangles differ in shapes and sizes depending on the design of the truss system, and they're primarily made up of equilateral and isosceles and right-angle triangles and all these mixtures. And so the question stands, but why triangles? Why are triangles used? Why don't we have squares? Why don't we have circles? What's some of the issues there? And I'm only going to be able to touch on some given the time of the presentation, but I'm going to try and at least give you an overview of how geometry has affected our engineering from, but in particular this area, but also in all areas of engineering as well. So, as we know, each triangle must add up to 180 degrees, and this can result in all kinds of different triangles, such as the ones shown to the right: equilateral, right angle, isosceles, scalene. There's heaps of different triangles out there, and despite all these different triangles, engineers tend to preference certain triangles over others, and you can see that in the image that I showed earlier. And one thing that you'll notice is equilateral and right angle triangles are one of the top ones that you use, with some scalene or sort of triangles working in where they can. But a good example of what I'm saying is in the Fink and Howe truss systems from the picture that I showed earlier. These all have equilateral triangles that stand in the center of the roof, with right angle triangles and isosceles triangles being attached to that center triangle. This shows that engineers tend to use these equilateral triangles at the center of their structure wherever possible. Now, the reason for an engineer's preference for equilateral triangles is rather simple. When a force is applied to the top of the equilateral triangle, the force is evenly distributed on both of the sides. This allows for predictable pressures on other supporting structures. The closer that one side of the triangle gets to being 90 degrees, say in a scalene or a right angle triangle, the more weight and force is distributed to that side that is leaning closer to that 90 degrees. This means that triangles with unequal sides will not only have its force distributed not have its force distributed evenly amongst its sides, but it also means that one side in particular is actually going to be getting the majority of it. They're pretty much the same statement there, but these two triangles therefore show that equilateral triangles are far more preferable for engineers when it comes to structural stability, because they're predictable. You know exactly where the pressure is going to be going. So in some cases, obviously equilateral triangles can't always be used. They're a very particular shape, and you can only, from an architecture point of view, you can only have particular roofing solutions. And oftentimes architects will just give an engineer a piece of paper, and the engineer has to come up with a solution to these different kind of shaped roofs. And so an example of this would be in the flat and sort of sloping flat roofing truss systems, as I showed to the right, but also in that previous picture. these roofing methods do not have the ability to fit an equilateral triangle within them, and therefore the structure relies on a mixture of these right angle and scalene triangles for structural support. Alright, right angle triangles seem to be used wherever possible, and you can see that in the majority of the truss systems shown earlier. This is because right angle triangles allow the majority of the force to be distributed to the one side with the 90-degree angle. As you can sort of see, if you were to push on that, you can see the majority of the force would push downwards with only some of it coming off to the side, and this means that the triangle doesn't distribute the weight evenly amongst its sides, but it's preferable for the force to be directed towards one side, and it's predictable for engineers to figure out where the force is going, and so therefore they can event construction systems accordingly. And this is hence why these triangles are used in truss systems that do not allow equilateral triangles to be used. So, given this understanding of truss systems and the way they work within the way geometry works within engineering, we can start to understand the way it works within other aspects of engineering other than just roofing solutions, which isn't particularly entertaining at all. So I've actually provided a mind map just here that shows all these different kinds of engineering that you can get into, and the way in which geometry is ultimately molded and has been used to manipulate the elements of Earth in order to, achieve a desired outcome. So, for example, let's take aerodynamics. As you can see, if you were to look through this, there's just a bunch of triangles that, speak out to me. In particular, this little nose here. And the reason for that is, again, it's distributed evenly. If we had a square there, it would just cause so much drag and so much tension on one side, there would be no way for that force to be distributed to the other sides efficiently, and so a triangle nose is used. Have you ever tried flying a square paper plane? It just doesn't work. And the same, even in the aeroplanes, you can see all these little triangles that are used as a way to support the structure of the plane. Bridge construction's another one. This is actually, imagine like a piece of land. This is what a truss bridge it's what it's called essentially. And so with this, you can see that triangles are used here. The suspension bridge, even over on the right here, it uses some weird kind of shaped triangle as a way to distribute the force of gravity. As I spoke earlier, there's these different kinds of truss systems for roofing solutions. Even in your manufacturing of engines and tools and equipment, you can see these different different kinds of geometry being used. But in particular, there's one system that I'm very familiar with, and that's residential construction systems. And we're actually encouraged to use geometry within architecture and this sort of construction side of architecture as a way to manipulate elements such as the rain, the wind, in a way that would make the house not only more structurally sound, but more efficient for cooling and that sort of thing. And even that is engineering in itself. And so obviously you can see how geometry has ultimately affected engineering, not only engineering, but even aesthetics and our ability to create, to build, and to discover new ways of doing things, to strive through to a greater humanity. And we will continue to rely on this knowledge in order to continue to build the wonders of the world, so to speak. And so thank you for listening to my presentation. Hopefully you enjoyed it, and hopefully it shows how geometry has ultimately affected all aspects of our life.